Hi, this is Dr. Austin Hitt, and welcome back to Into the Cortex. In this episode, we'll be taking a closer look at how System 1 processes information. We'll also start learning about how System 1 thinking generates science misconceptions. To begin, let's review how we humans make sense of the world around us. If you are not deliberately engaged in reflective, abstract, and logical thinking, your brain is processing information using System 1. System 1 compares attributes of the current situation to the information stored in long-term memory or schema. When a match is found, in whole or in part, a satisfying common-sense answer is produced. However, if the situation or phenomenon is significantly novel, then an internal alarm is initiated by the dorsal anterior cingulate cortex and it's set off. As a result, System 2 is aware that it needs to go into action. System 2 compares and contrasts the attributes of the present situation with a wealth of experience and knowledge stored within long-term memory. Through a more rigorous process of comparing and contrasting external physical world data with information stored in long-term memory, System 2 is able to devise a novel solution to a novel problem. Afterwards, the solution and the real-world consequences can be stored in long-term memory. As a result, the next time an identical or similar situation occurs, System 1 will have access to that information and can use it to respond to it. For example, you're walking down a sidewalk of a business district. The passerbys are mainly dressed in business attire. All is normal and System 1 proceeds as usual. Then, all of a sudden, you see a person dressed as a banana walking down the street. Suddenly you become aware of this discrepancy and System 2 engages and attempts to explain it. Maybe it's one of those silly birthday grams or the person is a street performer on his way to work. Now I'll show you an example in terms of science learning. On this glass dish, I've placed a small amount of fine-grained lycopodium powder. The powder is made from the dried spores of a club moss within the genus Lycopodium. For our purposes, the key attributes of the powder is that it's dry, fine-grained, and flammable. I can verify the flammability of it by checking the chemical label. Now I'm going to place a match on the top of this small mound of powder. What do you suppose will happen? Well, let's find out. I'll try again. Maybe there was just something quirky about how I placed the match on top of the powder. Well, that was disappointing. Maybe what is required is a different approach. Let's see what happens if we collect the powder in this straw and blow it over a candle flame. Would you like to see that? Again? Okay, here we go. So how did your thinking change throughout this little experiment? Initially, you probably anticipated the mound of powder would go up in one large flame. After all, I informed you the powder is flammable, and my assertion is verified by the label on the chemical container. When it didn't happen, you may have been surprised because it was your counter to your past experiences with substances like charcoal lighter or gasoline, which are flammable. However, the end result was clearly counter to your System 1 expectations. After the experiment did not proceed as you anticipated, your brain may have engaged System 2 to figure out what happened. You may have thought to yourself, maybe the powder was wet or the container was mislabeled. You also may have been surprised when the lycopodium powder ignited as it was blown across the candle flame. That is, of course, unless you thought I had a trick up my sleeve. If you were surprised, it's because your System 1 now had access to the previous experiment in which the powder did not combust. After you observed the powder ignite again, your System 2 may have become engaged in order to figure out why you might have produced such a bright yellow flame. The solution is oxygen, or more accurately, the relative amount of oxygen within the proximity of the powder. You may recall from grade school science that in order for something to burn or combust, you need oxygen. In the first situation with the mound of lycopodium powder, oxygen was mainly in contact with the powder at the surface of the mound. You may have noticed that there was some light charring at the surface of the powder. In the second situation, when the powder was blown through the straw and across the flame, it was in contact with many more oxygen molecules. The higher concentration and greater contact between the lycopodium powder and oxygen molecules is what allowed the powder to combust. I now want to address where the information used by System 1 comes from. The accumulation of experiences and knowledge starts early in life. In fact, it starts almost immediately after we humans are born, and it continues from infancy on through adolescence. The brains of human infants are constantly gathering information about the world. This is because they have very limited knowledge about how it works. For example, basic ideas and experiences that adults take for granted, such as ice is cold and rocks are hard, and the fact that objects fall downward when dropped instead of being suspended in midair, are all phenomena that infants have to learn. However, it should be pointed out that the brains of human infants are not blank slates either. Like a computer or a smart television set, the human brain comes with presettings. In the case of humans, these settings produce preferences in the way the brain interprets the world around us. The human brain presentence functions as heuristics or algorithms for solving problems. I'll now elaborate on two such heuristics, pattern seeking and agenticity. There are actually many more such rules of thumb which facilitate decision making. I'm focusing on these two because they have been demonstrated to have a significant and negative impact on science learning. First, the human brain is wired to seek out patterns in the world around us. This is actually a good thing because it helps us identify patterns and routines in the external world. For example, it's useful to know that biting mosquitoes come out to feed on the cover of their dusk. This information can help you avoid mosquitoes and their painful bites. At dusk, you know that you can come indoors or put some repellent on in order to repel those pesky mosquitoes. Now, I'd like for you to take a few moments and examine the image that pops up on the screen and note what you see. Are you ready? Go. Did you see anything? When I've shared this image with my students, they often tell me they see something akin to a bug, a horned animal like a ram, or some type of monster or alien. A feature that commonly grabs people's attention are the two symmetrical dots near the center of the image, which are often interpreted to be eyes. In reality, the painting does not contain any image, at least not one that was intentionally constructed. My daughter made it. She did it by dabbing a blob of paint in the middle of a piece of paper, folded it in half, and then randomly pressed against the sides of the paper. When the paper was reopened, voila, the image you see on the screen emerged. Your brain, System 1, and predilection for patterns did all the rest. When you examine the paint splotches, System 1 accessed long-term memory in search of similar images and information. Whatever images System 1 found most relevant, and it varies from individual to individual, is what popped into your thoughts. Now I'm going to address the heuristic of agenticity. It is the internal rule of thumb that directs the brain to attribute natural phenomena to causal agents' innate drive or purpose. Let me provide you with an example that will show you what I mean. Imagine you are walking in an old wooden house. As you stroll through the house, you hear all kinds of creaky and crackling noises. Your first thoughts may be that the noises are caused by someone or something, a ghost perhaps, moving throughout the house. Your brain System 1 likely accesses a plethora of scary ghouls and goblins and alien images that are stored within long-term memory. These images are obtained from a variety of sources such as television, movie, comic books, etc. System 1 uses such images stored in long-term memory in order to generate a quick and inaccurate explanation of the phenomena. Whew. After a few seconds, you begin to think about the situation more deeply via System 2. You can then recall that it is normal for a house to creak at night. This is because during the daytime, the wooden beams and the metal nails in the framework are heated up and expand under the sun's rays. However, once the sun sets and as the temperature drops, the materials comprising the structure of the house cool down and contract. It is this concurrent cooling and contraction of the house's materials that produces the creaking and crackling sounds, not ghost. Wow, that makes more sense. Now I want to show you how the brain's application of the heuristics can produce erroneous explanations and misconceptions about the world. I'll provide you with two final examples. First, imagine that you're simultaneously rolling 4 dice, which results in these rolls. Do any of these rolls seem more or less probable than others? Well, if you're like most people, your eyes focus on the roll with all twos. It probably felt improbable and unlikely. If you receive such a roll, you might think, wow, what an extraordinary stroke of luck. Well, the chances of obtaining such a roll are actually 1 in 1,296. That's pretty long odds. But wait a minute. The same odds also apply to the other two rolls. However, your brain system won't focus in on the all two sequence because it looks like an unusual pattern. In reality, all of these sequences are equally probable. This preference for patterns can lead to erroneous conclusions in the context of a science class. For example, during an inquiry lab or a field investigation, students may find patterns in their data that are not real, but just reflect random fluctuations. And the pattern-seeking heuristic is not just a problem for science students. Empirical research reveals that even scientists are susceptible to this heuristic. Given short time period or cognitive overload, they too can make the same mistakes. For my second example, I'm going to ask that you read the following list of statements and identify which ones you believe are scientifically accurate. Are you ready? Go. It is likely that most of the statements you read seem pretty accurate. But actually, only 3 are truly accurate scientific statements. Those statements are: plants use sunlight to make their own food, flowers wilt because they are dehydrated, and bread rises because it contains yeast. So what's wrong with the remaining statements? The answer is that all of them incorporate the idea of purpose or intentional actions on behalf of an agent or an entity. Take the statement that mosses form around rocks to stop soil erosion. While it is true mosses can prevent soil erosion, that's not the reason they grow on rocks. Mosses grow on rocks because that's where they live. That's their niche. The fact that mosses can prevent soil erosion is just coincidence. Likewise, in science classes, students often exhibit a proclivity to explain the natural world as having some purpose, design, or some sentient agent being responsible for it. Psychologists refer to this phenomenon as teleological thinking, and under the right conditions, such as cognitive overload or short response period, even scientists are susceptible to teleological thinking. As you go back and review the other statements, you will see that all of them infer some type of intentional design or purposeful action. The intuitive appropriateness of these statements is directly related to the brain's predilection for attributing phenomena to the action of causal agents. In the next episode, we will examine how most of the fundamental information that we receive about the natural world, information gleaned by our 5 senses, is very often inadequate for generating accurate, causal, scientific explanations of the world. Until next time, keep on sciencing.